So today we'll focus our attention on coordinate systems, section 4.4. Um, so first of all, let us look at the definition. What is coordinate, B coordinate means, or what is this coordinate system all about, okay? Suppose B is a set and it has two vectors B1 and B2, which is a basis for a vector space V. Meaning vector space V is actually created by some linear combination of B1 and B2. And let's say X is in V. Okay, X is an object in that vector space V. The coordinate of X relative to the basis B, it is sometimes called as B coordinate of X, are the weights, or you can say scalar, C sub 1, C sub 2, all the way up to C sub n, such that X equals C sub 1, B sub 1. Actually, this B is not B1, B2 only. So I'll write this as B1, B2, Bn. Okay, so that's the basis. Now, X, it can be written as C1, C sub 1, B sub 1 plus C sub 2, B sub 2 plus all the way up to C sub n, B sub n. Now, in this case, you see X is an object in V. Then when we write XB, this is the object in Rn. And what it means is we just write the scalar like that. Okay. We call it B coordinate of X is defined to be this way. Now, what it means is, for example, X equals, 2B1 plus 3C 3B2, for example. Then if I write X sub B, what it means is 2 and 3. Just write the scalar. Okay, it's weights. This is called B coordinate of X. Now here X is in V vector space B, whereas X B coordinate of X belongs to Rn. In this case R2, because there are only two objects, so we can say that XP belongs to R2. That's how we define the coordinate vectors. Now, let us look at graphically what it means. Here is one example. Consider the vector V1, which is given by 3 and 1. And V2 is another vector given by -2, 1. Here B1 and V2 are linearly independent and span R2. So B is a set that has these two vectors V1 and V2, which is actually the basis for R2. That means R2 can be generated by some linear combination of these two vectors. Now, let us suppose that X is 4, 3, write B coordinate of X. That is, find B coordinate of X. Part B, if XB equals 2 and 1, that means, this is actually C1, C2, find X. Now, let us look at this graphically, what it means. Now, you can see the graph there, right? So I use two different colors to represent. My X is right here. This is my X. Okay. So my X is, can you tell me what is the coordinate for X? Using the green, the standard graph, because there are two kind of graph. One is the standard graph where I use the green color to make that graph paper. Okay, so if I look at this X from green, if my graph is the green line, green color graph, then you see my vector is this green, represented by green. That means 1, 2, 3, 4. Okay, so x is 4 and my y is 1, 2, 3. So y is 3. Done. That is my x. Now, what is my xb? I mean b coordinate of x. Now, in this case, the red vector represent the b vector, okay, the red color. Now, use the red color and tell me what is the, how can we represent that x using the red vector? So red vector means this is 1, and then again here from here to here, this is 2, okay? So I have 2, and then here this one is 1. So 2 and 1. So the b coordinate of x is 2 and 1. Now see the difference. In this case, it is the standard graph, okay? And then we just use the green vector, this green here, 1, 2, 3, 4, and then y-axis, the another direction is 1, 2, 3. So 4 and 3. Now for b coordinate, I'm using the red color, which is 2 and 1. That's it. Any question? So I believe that if you are given the graph like this, then you will be able to figure out what is the b coordinate of x. It's not that difficult. But you know what? Life is not that always easy, right? Sometimes they do not give us the graph, but they just give us the vector. Then how do we find out the b coordinate of x? Or if we are given the b coordinate of x, how can we find the standard coordinate for that vector? So that means we need to come up with some algebraical rule, algebraical process. And that's what we're gonna do now, okay? So if suppose we are not given the graph, then how do we do that? Let's look at this now. Right, so by looking at the graph, we already got the answer for part A and part B. Part A, b coordinate of x is 2 and 1, and then the if b coordinate of x is 2 and 1, what is x? We already found 4 and 3. Now we are going to develop a process, algebraical method, when the graph is not given. How do you do that? Okay, listen very carefully, okay? If you know how to do one problem, you will be able to handle similar problem easily. So in part A, we need to find xb, which is actually, we know that c1 and c2. To find this, what we're gonna do here is that to find xb, consider x equals c1 b1 plus c2 b2. Let me write in another way. Just give me 1 second. I think the language, let me write a better language here. So here we find C1 and C2 such that x equals C1 B1 plus C2 B2, right? Because B1 and B2 is the basis and C1 and C2 are actually the scalar. So that's what we want to find. So that means C1, B1 is already given. Oh, not B1, V given, sorry. This is V, B1, B2. B1 and B2. We represented that basis vector by B1 and B2, and that's fine. So B1 we already know, which is 3 and 1, plus C2, V2 we already know, which is negative 2 and 1. Okay, and what is given in part A is that x is given. So that means x is given, which is 4 and 3. I can write that like this. Now this one, you can write this one as 4, 3 equals 3c1 plus, not plus, minus 3 minus 2c2 1c1 plus 1c2. So what it means is, this means 3c1 minus 2c2 equals 4, and 1c1 plus 1c2 equals 3. This is equation 1, this is equation 2. All we need to do is we need to, solve this two equation. Can you please solve and let me know what is the answer? What is C1 and C2? Solving this system of equation, we get C1 equals 1 and C2 equals 2. This is what we got earlier when we look at the graph, right? That's what it is. Now, I don't know how you solve it. There are different ways to solve it, but just, let me just write down this in matrix notation, okay? So in matrix notation, so what I can write here is that I can write this as 3, -2, 1, 1, and then C1, C2 equals 4 and 3, right? I can write this way. And then you can solve it. You can consider the augmented matrix. So augmented matrix is 3, 1, -2, 1, and then 4 and 3, and then solving this, changing into echelon form, changing into echelon form, and then you will get, and then finally you get C1, C2. This is your C1. You will get 1, 0, 0, 1, 1, 2. This is what you will get. This is your C1. This is your C2. So therefore C1 equals 1 and C2 equals 2. Or you can simply use your high school method to solve that system. It doesn't matter what you do. Now, one very important property that I want you to observe, very important property, okay? I will write this as PB. This one, we already know that this is our B coordinate of X, and this one is X. Now we have the formula, you see. So the formula is, this is called change of coordinate matrix, by the way. Okay, this PB, this is called change of coordinate matrix. Change of coordinate matrix, and this is called B coordinate of X, and this is simply X. Now please remember this formula. We can use that formula as well. Okay, part A is done. Now let's look at part B. In part B, what we are supposed to do is XB, B coordinate of X is given, and we need to find X. Okay, in part B, given, let me just go all the way here. In part B, given B coordinate of X, which is 2 and 1, . Oh, by the way, this is 2 and 1, right? I think I made a mistake here. So this is 2 and this is 1. Sorry, I messed up. I messed up. So this is C1 is 2 and C2 is 1. Okay, please make necessary correction here. C1 is 2 and C2 is 1. Okay. All right, so this is given. That's what we found earlier. So this is given, and what we have to do here is, what it means is, this means C1 and C2 is given, and we need to find what? Find X. That's the question, right? So we know X is actually C1 V1 plus C2 V2. We know that. So that means C1 is 2, B1 we already know. So B1 is 3 and 1 given in the question. Plus C2 is 1, V2 is already given, which is negative 2 and 1. So if you work it out, so you're going to get 6 and 2 plus negative 2 and 1. So you're going to get 4 and 3. Actually, that is what we got earlier. Look at that. By looking at the graph, that's the thing we got. Now, part C is find the change of coordinate matrix PB from B to the standard basis in R2. That's what we already found in A. And use it to find X in B. Okay. Part C. Change of coordinate matrix is written as PB equals, we already found it, it is always V1 and V2. Okay, whatever the basis is given, that's what it is. So that means B1 is 3 and 1, V2 is negative 2 and 1. This is the same thing that we got earlier. You look at, okay, this is the change of coordinate matrix. Basically, this one is V1 and this is V2. You can directly write that V1 and V2 if you like. And the question says use this to find what? Use this to find use it to find X. Okay, using that we'll find X. So we know the formula already. So look at this. What we got here is that this is our formula now. You can consider that as formula. X equals PBX B coordinate of X. So we know X equals change of coordinate matrix and then B coordinate of X. This is the formula, and let us calculate that. Let us use this formula to find X. We already know how to find X by this method, but we're gonna learn, the formula, another method here to find X. So this guy is 3, negative 2, 1, 1. And XB, we already know XB, which is 2 and 1. So now please multiply this. If you multiply these two matrices, you're going to get 4 and 3, right? That's it. Now part D. What we are supposed to do in part D? Find PB inverse, change of coordinate matrix PB inverse from the standard basis in R2 to part A and use it to find XB. Okay. Now let us develop the formula first before we do this. Okay, here formula development. We already know X equals change of coordinate matrix PB and XB. Now left multiplying both sides. Both sides by PB inverse, we're gonna get PB inverse X equals PB inverse PB XB. So PB inverse X equals, this guy becomes 1, you see? So B coordinate of X. So that's another formula. Now remember, we got two formula here. This is our formula number 1. And this is our formula number 2. So let me just write it down this way. XB, B coordinate of X, is actually this one. Let me write this as formula number 2. So in part D, the question tells us that use this formula to find XB. Now let us use that formula. So the formula is B coordinate of X equals change of coordinate matrix, inverse of change of coordinate matrix PB X. Now we need to find the inverse of this guy, 3, 2, 1, 1. Find inverse of that, and X is 4 and 3. Can you please find the inverse of this matrix quickly? So you already know how to find the inverse of 2 by 2 matrix. It's pretty easy. Let me just remind you if you forget. So let's say we have A, B, C, D. Inverse, how we find the inverse is actually 1 over AD minus BC. And then we switch that D here, A here. We change the sign C, negative C, and negative B there. That's it. So by doing that, I'm going to get 1 over 3 minus plus 2, and then this will switch 1, 3, and negative 1 and positive 2. That's it. 4 and 3. So it will give me 1 over 5. And then when you multiply this 2, so how much do you get? You will get 10 there and 5 there. If you multiply these two matrix, you're going to get 10 and 5, which means 2 and 1. Okay, this is the exact answer we got earlier, right? So now we have many different methods to do it. One method is, if we are given a graph, we can just look at the graph and find the answer, or we can use the technique that we use in A and B, or we can use the technique that we use in C and D. And I want you to try one questions on your own, okay? Okay, so in example 2, we are given a basis vector v1 and v2, which is 2, 1, and 1, 4. And in part A and C, we need to find the change of coordinate matrix xb. Okay, let us work it out. We know the formula, right? So we know the formula here is xb equals PB inverse X. That's the formula. And X is also given. When X is given here in part A and C, X is 7 and 3 is given. X is given. Okay. Now all we need to do is PB inverse is actually, we know that PB inverse means it's just like you just write down those two vectors here, 2, 1 and 1, 4. Find the inverse of that and then multiply with 7 and 3. All you need to do is this. Okay, so that means 2, 1, 1, 4, the inverse of this matrix. I trust that everybody will be able to do it. So it's going to be 1 over 2 times 4 is 8 minus 1. And then we'll switch that 4 and 2 there, and then negative 1 and negative 1. And then, so 7 and 3. So that's going to give me, if I, that's 7, 1. So basically, you're going to get 1 over 7. Anyway, So if you complete this, then I leave it to you, and the final answer would be, can you tell me what is the final answer there? Okay, yeah, all right, thank you. So when you simplify this, when you multiply these two matrices and then divide by 7, you're going to get 25 over 7 and then negative 1 over 7. All right, so part A and C is done. Now part, I'll write this way. This is part A and C done. Now part B and D. So part B and D, what is given here is that given the B coordinate of X is given, which is 1 and 3, and find X. So we know the formula, right? So the formula is X equals PB, change of coordinate matrix B, and B coordinate of X. That's the formula. And we know that PB, change of coordinate matrix, is made out of these two vectors, which is 2, 1, 1, 4, and XB is already given there, which is 1 and 3. So if you multiply that, some of you already got the answer in the chat box. That's great. And so if you multiply, you're going to get 5 and 13. So when you multiply these two matrices, that's what you got, 5 and 13. And that's the X. Okay. That's it. Now we focus our attention on, anyway, we will be working now on
I have a question.
one of the really good benefit or application of this coordinate system is that we can, we can change unfamiliar coordinate system into familiar coordinate system. So we can change, we can work with different kind of coordinate system, and we can change from one to another whenever we need it. Okay, so we can change unfamiliar system into familiar system. That is one of the most important application of this coordinate system. Now let's look at example 3. And in example 3, let B is a basis, 1 to be a basis of polynomial of degree 1. Okay, actually this is the standard basis for polynomial of degree 1. Polynomial of degree 2, the standard basis is 1t square, because remember the P2 is of this form. So C1 1 plus C2t plus C3t square, that is a polynomial of degree 2. That is the standard form of P2. And this is P1 means, C11 plus C2t. So this is the standard form of polynomial of degree 1. Okay. B, the basis is given. And part A, what is PB? Part A. What is PB? I mean, B coordinate of P. If the question is find B coordinate of P if the expression, the polynomial given is 3 minus 2t. Now, there are a couple of ways to do this. I think the easiest one in the case of polynomial will be this one. Remember what we said earlier is that X can be written as C1b1 plus C2b2. So in the same way, here we can write P of t equals 3 minus 2t equals C1b1 plus C2b2, which means now compare this. B1 is what? B1 is here. Look at that. B1 and B2, they are the bases. So we can write this as C1, B1 is 1 plus C2, B2 is T. Now when you compare this, so comparing, we get C1 equals 3 and C2 equals -2. So x coordinate of P coordinate of B can be written as 3 and -2, because remember this how we define. By definition, this means the C1 and C2, which is 3 and -2. That's it. Now from now onwards, if you are given a polynomial, let's say P of t equals 3 plus 4t plus 5t squared, then if you want to write B coordinate of P, what all you need to do is just the constant, just the scalar, 3, 4, 5. That is the B coordinate of P. Okay, this belongs to polynomial, but this B coordinate are actually the scalar which belongs to Rn, in this case R3. This is P2 and this is R3. Okay, that's important point to remember. Now, if PB equals -1 and 3, what is PT? So in part B, given PB equals -1, 3, which means we already know that this is C1 and C2 by definition. So this gives me C1 equals -1, C2 equals 3. So all we need to find is P of t. So P of t is actually, we know by by convention, this is C1 B1 plus C2 B2. Substitute the value. C1 is -1, B1 is 1, plus C2 is 3, B2 is, what is B2? B2 is t. So that's going to be -1 plus 3t, done. Okay, now let's let's talk about one very important concept. This is what we call isomorphism. Okay, isomorphism. What does that mean? A one-to-one linear transformation from a vector space V onto a vector space W is called an isomorphism from V onto W. If such a mapping exists, then V is isomorphic to W. So in other words, we call a one-to-one and onto linear map of vector space an isomorphism because the two spaces have algebraically the same structure. So before we talk about isomorphism, then we need to know this one. Actually, I believe you did this in your high school or in your pre-calculus or some math class. So onto mapping means this is your domain, this is your range. Okay, onto mapping means in the domain there should be no one left behind. Okay, everyone should have a pair there. But onto means none of them is left behind, but there are some in the range in R where it is associated with two or more than two members. This kind of mapping is called onto. It is not one-to-one. Okay, onto but not one-to-one, because there are two guys going to the same member here. Two member from D is going to the same one member there, so that means it is just onto but not one-to-one. Now one-to-one mapping is, this is going one-to-one, but there is some in the range, and this little guy here in the range doesn't have anyone to go with. Okay, it is left behind. So this kind of mapping is called one-to-one, but not onto, not onto. And this mapping is called one-to-one and onto. It is one-to-one and onto. And the special word that we use is um, bijective. Okay. And so this kind of figure is called isomorphism. So this means D and this is R. So they have, whatever properties these guys satisfy, and the same property here. So how many members are there? The same number of members are there in R, in D and R, in domain and range. This is what we call one-to-one and onto. So this is called isomorphic. Okay, D is isomorphic to R. You can write that. Now, let's look at a few examples. Oh, by the way, let me just tell you one thing. Now, if you are given, let's say, polynomial, let's say 2 plus 3t square. So find b coordinate of p. How do you find? Well, what you do is you just write down this as 2 plus 0t plus 3t square. So your b coordinate will be just the constant, okay? Just the constant c1, c2, c3, which means some of you already got the answer there. Thank you. 2, 0, 3. In the same way, if you are given a matrix, let's say A, B, C, D, okay? So if I ask you find b coordinate of A, then this means it will be A, B, C, D. You just write that way. That is the b coordinate of A. All right. So now if you are given, let's say C equals 1, 0, 0, 2, for example, then if you want to find b coordinate of C, all you need to do is 1, 0, 0, 2. That's it. Now the beauty of this coordinate vector is that using this vector sometimes to prove whether the given vectors are linearly dependent or independent is pretty easy. First of all, let us do example 4 and then example 6 and 7. Example 4, so that the polynomial of degree 2, that is P2, is isomorphic to R3. Example 4, let's complete that. So P2, so let us suppose that P of t belongs to P2, polynomial of degree 2. So our P of t can be written as C1 1 plus C2t. Remember, P2 means plus C3t square. So this is polynomial of degree 3. So this is the standard form. Any object which is polynomial of degree 3 can be written that way. Now, if you want to find b coordinate of P, all you need to do is C1, C2, C3. Okay, that's it. Now, where does this belong? This belongs to R3, right? So clearly, any vector of this form, C1, C2, C3, belongs to R3. So it's proved. So we can write, so P of t, polynomial of degree 2, polynomial of degree 2 is isomorphic. It is one-to-one, by the way. One-to-one and onto. So do polynomial of degree 2 is isomorphic to R3. Okay, in the same manner, if you are asked, prove that polynomial of degree 4 is isomorphic to polynomial of degree 3 is isomorphic to what? Can somebody tell me? P3 will be isomorphic to? P3 means the standard object for P3. Anything that is in P3 will be C1 plus C2t plus C3t square plus C4t4. Sorry, T3, right? That is polynomial of degree 3, standard form. So what is the B coordinate is actually C1, C2, C3, C4. So all we can say is that this belongs to clearly R4. So polynomial of degree 3 is isomorphic to R4. So you can prove that way. Not a big deal. So I'll provide the, you try this example 5 and 6 yourself, and I'll provide solution in my lecture note for example 5 and 6. Example 7, I just want to give you one hint, and I think you'll be able to solve it by yourself. In example 7, use coordinate vectors to show that the following vector S is linearly independent. So there are many ways to prove this, but if you want to use the coordinate vector to prove this linearly independent, all you need to do is this. Let's say, guys, give me 2 minutes and we'll be done. Let's say this is my B1, this is B2, and this is B3. Or maybe I can write ABC if you like. A, B, C. Now, all you need to do is, oh, not ABC because we write B coordinate there. So let me write ACD. So now B coordinate of A will be 1, 1, 0, 1. B coordinate of C is negative 2, 3, 4, 5. And B coordinate of D is 0, 6, 7, negative 4. Okay, and now to show that this is linearly independent, all you need to do is now to show S is linearly independent, consider a matrix 1, 1, 0, 1, negative 2, 3, 4, 5, 0, 6, 7, 4, and then change it into echelon form. Change into echelon form. And then I trust that you will be able to change it into echelon form, and you do all the way whatever, and the echelon form will be your echelon form will be something like 1, 0, 0, 0, negative 2, 1, 0, 0, 0, negative 1, 0, 0. So you see there are two pivots. This is our pivot, this is our pivot, but there is a free variable. Okay, there is a free variable. So since there is a free variable, the set, because you see the coordinate vector and the matrix are isomorphic. They are 1 to 1 and on 2. So whatever property, linearly dependent or independent, this guy right here, the coordinate vector has the same property we'll have with S. So they have the same property, okay? We notice that the coordinate vector are linearly independent, therefore the set is also linearly independent. Just keep that in mind. This method sometimes make life a lot easier. Since there is a free variable, the set is linearly dependent. Okay, so we're gonna do a couple of questions similar to this in our next class. All right.